Hi, today I'll be talking about piezo-1, which is a protein located in the plasma membrane. So piezo-1, in addition to being a transmembrane protein, is a mechanism-sensitive ion channel, and its function is activated by applying pressure to the lipid bilayer. So it plays a key role in sensing mechanical forces like shear, stress, and stretch, and within the cell, it may be found in the endoplasmic reticulum, cytoplasm, and the nuclear envelope. So some of the cell types where we can find piezo-1 include endothelial cells lining blood vessels, red blood cells, and epithelial cells in the kidney and the lung. I also discussed a disease of piezo-1 called dehydrated hereditary xerocytosis or DHX. Now let's delve deeper into the piezo-1 structure. So the overall three-dimensional shape of piezo-1, its tertiary structure is a three-bladed propeller-like shape. So here let me move my camera, I show the three blades of my model in blue, pink, and green. And so piezo-1 channel is a homotrimeric oligomer with three subunits that assemble to form a central pore for ion transfer. So in addition to the extracellular blades, there's a central cap that's also extracellular. Um, and the primary structure of piezo-1 comprises over 2,500 amino acids and 38 about transmembrane segments. So the transmembrane structure has a helical topology. I showed the helices here for with yarn. Um, and the helices span the cell membrane and are crucial for piezo-1's function as a mechanosensitive ion channel. So now let's look at how mutating piezo-1 affects its structure. So the mutation associated with DHX occurs on amino acid 2456, which is located on the C-terminal end of the protein. And from research, we know that this is in the cap region because the cap structure is formed by the large C-terminal extracellular domain, and it comprises amino acids 2210 to 2457. So the mutation involved is actually um, a heterozygous substitution R2456H, where G is changed to A from arginine to histidine, so AGG to CAC at amino acid 2456. In normal piezo-1, some of the properties of arginine are that it's polar in charge, it's more hydrophilic than the 19 other standard amino acids, and because it's the third largest amino acid, it's comparatively large sized. This allows it to participate in interactions like hydrogen bonds via the guanidinium functional groups, salt bridge formation, and cation pi interactions. In mutated piezo-1, however, histidine proteins include that it is still polar, positively charged, and hydrophilic, but it's now smaller than the original amino acid. Some of the interactions that histidine can participate in include hydrogen bonds, pi-pi stacking interactions, cation pi interactions, and coordinate bond interactions with metal cations. Now let's look at the effect on the protein function. Under normal circumstances, piezo-1 senses mechanical forces applied to the cell. These forces may come from inside out or outside in. And the cell membrane, after being mechanically stimulated, the pressure eventually converges on the piezo-1 channel. The piezo-1 channel undergoes a change of state from closed to open, and then allows the flow of calcium, potassium, and sodium ion plasma. The cell converts the mechanical forces into signals in the cytosol that regulate the volume and shape of the cell. And this is needed for organisms' functions like blood vessel formation, vascular structure, and morphogenesis of muscle cells. R2456H is a gain of function mutation because it leads to heightened permeability to cations and impaired ion flow. It also results in altered sensitivity to mechanical stimuli and affects force transduction. And the effects on the cells include elevated hemoglobin levels and premature breakdown of red blood cells. Effects of the mutation on organisms include anemia, blood pressure, and circulation issues, as well as impaired function of the kidney. Now to some limitations of my model. So to start with, the straight edge and cylindrical shape of the model right now, straight edge, cylindrical, it's not representative of the true blade-like, propeller-like structure of piezo-1, and especially because the transmembrane region in the actual piezo-1 is bent with a pronounced curvature. Also, the location, I know we talked about it being in the cap, but this is just approximate because it's not exact because my model's resolution is three-dimensional, not at the amino acid level. Also, I don't show the change in size from larger to smaller in my model. Finally, the chemical properties and bond formation in piezo-1 is not represented in the current version of my model. Thank you.